Hi, this is Dr. Xu teaching mine ventilation for mining engineering college students. Today we will talk about underground mine heat. Heat is emitted into subsurface ventilation systems from a variety of sources. In most of the coal mines, the airstream itself is sufficient to remove the heat that it produces. In deep metal mines, heat is usually a dominant problem and may necessitate the use of refrigeration plant. Conversely, in cold climates, the intake air may require artificial heating in order to create conditions that are tolerable for both personnel and equipment. The three major heat sources in mines are the autocompression, machinery, and geothermal heat from strata. The geothermal heat from the strata is the most complex to analyze in a quantitative manner. For detailed method for analyzing geothermal heat from strata, please refer to chapter 15.2 in this book. You can download the PDF file from the link listed on this slide. Let's look at autocompression. As air falls through the downcasting shaft, it converts the potential energy to thermal energy, resulting in an increase in temperature. So temperature will be increased here. Generally, the wet bulb temperature increases 4 to 6 Celsius degree per kilometer depending on surface air temperature, and dry bulb increases 9.8 Celsius degree per kilometer, but it depends on evaporation rate. The reverse effect, air goes from the bottom of the mine up to the shaft and goes to the surface. It's called auto-decompression. Auto-decompression occurs in upcast shaft. This is usually of less concern as upcast air leaves the mine and have no effect on working conditions in underground. However, the reduction in temperature due to auto-decompression in upcast shaft can result in condensation and fogging. The mixture of air and water droplets may reduce the life of the exhaust fan at the shaft top. Let's look at this example. Air enters a 500-meter deep shaft at 20-degree wet bulb temperature and 25 dry bulb temperature and 100 kilopascal pressure. What is the dry bulb temperature at the bottom of the shaft, assuming no frictional losses and adiabatic conditions exist? So there's no heat transfer from surroundings to air. An air thermal capacity is given as 1.029. To solve that question, we need to introduce the term enthalpy. Enthalpy is an abstract concept for energy. It equals to internal energy, which depends on temperature plus air pressure multiplied by air volume. So enthalpy is an abstract concept for energy, and it is impossible to calculate the absolute enthalpy, and we are only interested in changes in enthalpy. For ideal gas, enthalpy is a function of temperature only. The change in enthalpy equals to the thermal capacity of air by the change in dry bulb temperature. Normally, thermal capacity is known as 1.029 kilojoules per kilogram Celsius degree. Based on steady flow energy equation, we have this equation. The change in enthalpy equals to the change in height above datum by gravitational acceleration by heat added from surroundings. We can use this equation and this equation to solve the problem. So in this problem, we have a shaft. We can define here as position 1 and here as position 2. To calculate the change in enthalpy, H2 minus H1 equals to Z1 minus Z2 by gravity by Q. In this question, Z1 minus Z2 is 500 meters, and G can use 9.81, and Q is 0 because there's no frictional losses and no heat transfer. So we can solve H2 minus H1 equals to 4.905 kilojoules per kilogram. In the second step, by using the relationship between enthalpy and dry bulb temperature, we have H2 minus H1 equals to air thermal capacity by T1 minus T2. This is 4.905. This is given as 1.029. T1 is, that's the dry bulb temperature at the surface, 25. We can solve T2 equals to 29.77 degrees Celsius. That means air with 25 degree of dry bulb temperature goes down the shaft. At the bottom of the shaft, its dry bulb temperature is increased to 29.77. Thank you very much for watching. If you like the video, please give it a thumb up, subscribe to the channel, and share it to others. We will talk about heat from machinery in another video.